Greetings, dear virtual attendees of the first European Conference on Fracture to be carried out online. My name is Manuel Sardinha, and today I will present to you the primordial work done for a study that aims to understand the influence of seams in the mechanical properties of PLA parts produced with multiple extrusion modules. This presentation starts by giving context and motivation for the study, explains some of the experimental and conceptual steps carried, and concludes with further works being developed on the subject. As for me, since September 2019, I am a PhD candidate at Técnico, which is a strictly engineering faculty integrated in the University of Lisbon, Portugal's capital. This study was developed inside a fairly recent laboratory in Técnico, Lab2Prod, the laboratory for product development. Its official foundation dates back to 2006, and its focus is divided into product development, material characterization, novel design methodologies, and the mechanical project of additive manufacturing machines. The work that laid ground for this study is associated with the 2016 patent, and this year we are trying to evolve that patent into a startup, Fab Inventors. Briefly, both this patent and study deal with the specific manufacturing process, material extrusion, better known for some as fused filament fabrication or fused deposition modeling. In this manufacturing process, heated feedstock plastic filament passes through a nozzle tip and is then deposited into a build platform, creating tailored structures layer by layer. Material properties can vary widely, and parts are often considered to be anisotropic. Among the multiple process parameters that can influence components' behavior, we can name build orientation, layer height, and temperatures involved. The motivation for this study comes, broadly speaking, from the potential of these additive processes as disruptive technologies that can transform industries, shorten product development steps, and considerably reduce components' time to market. Adding to this, a slightly different source of motivation arises with the specificity of works developed at Lab2Prod. Namely, in the figure on the right, there's a picture from 2017 of my master thesis, a dedicated material extrusion apparatus. The apparatus consists of two independent extrusion modules that allow a parallel and collaborative fabrication of parts. To control it, a dedicated slicer software that avoids collisions between modules is used to generate the G-code file. This software slices the model into layers and in each layer allocates a percentage of the area to be produced by each module. Since 2017, numerous iterations, machine versions, and tests were performed. The left figure displays a new multiple extrusion apparatus that was developed by the research team, and on the right we can see a render of the most up-to-date version of the machine used for this study. Recently, the project has even received some attention from the Portuguese media. You can find more at fabinventors.com. The manufacturing of parts through multiple independent and collaborative extrusion modules emerges as a potential solution to overcome the limitations of speed, cost, and scalability of the established AM processes. By allowing a collaborative manufacturing between extrusion modules, the size of build parts can increase without compromising production time and maintaining geometrical accuracy. The existence of multiple independent extrusion modules imposes the existence of intersection areas in parts, and these intersections can be better understood as seams. In this work, authors take advantage of the dedicated manufacturing apparatus and slicer software to evaluate the influence of seams in the mechanical properties of PLA dog bone type samples produced with two independent extrusion modules. Four different types of specimen were produced, differing in seam dimensions as demonstrated in this scheme. They were produced with seams varying in size between 0 mm and 20 mm. It should be underlined that toolpaths are generated for each layer at a time. On the seam area, the contour of the part is generated with the negative offset of the part's boundary and then cut by the seam line. The infill is generated for each area with an intersection with a set of equally spaced lines. Therefore, the intersection in each layer is achieved by intersecting contours over contours and infill over infill like it was with a single extruder. During manufacturing, each layer alternates between figure A and figure B. All specimens are produced with a raster angle of 45-45 degrees, a layer height of 0.2 mm, a nozzle with a 0.4 mm in diameter, and at a 205 degrees of extrusion temperature. The material chosen for the study was PLA, polylactic acid. It is a semi-biodegradable thermoplastic polymer, and one could argue it is the most used filament for this type of material extrusion. Two spools of white PLA filament were used in this study. The spools have a consecutive manufacturing lot number, and their filament diameter is 1.75. The standard test method used follows the specifications from the standard ASTM D63814. The tests were performed on a universal testing machine with a 10 kN load cell and a crosshead speed of 2 mm per minute. Here we show two broken specimens after the tensile test. From the fractured surface, it is possible to observe that specimens with seams display a smoother surface than specimens without them, and that the fracture location is always in one of the ends of the seam when there is one. Samples manufactured without a seam continued to sustain the applied load, undergoing plasticity, denoting the tearing of the extruded paths, while in samples with seam, rupture of the specimen is coincident with the elastic limit of the material, the surface is uniform, and separation of paths that were deposited with different printheads seems to be present. On the bottom left, we can see test specimens without seam, and the bottom right, we see a test specimen with a 10 mm seam. Here we can see the dimensions of the specimen and some of the study results. On average, tensile strength of specimens with a seam is 7 to 12% lower than specimens without one. Seam dimensions show to have little influence on the tensile strength of specimens. Concluding, the results suggest that in material extrusion, seams act in a part by creating a localized fragility, diminishing its properties. The maximum stress achieved in the specimens with seams is coincident with the elastic limit of the material. Accordingly, seams could be considered in the design stage of a product since their location and placement can act as a mechanical fuse. The results lay ground for further studies on the subject, which can be focused on seam properties, geometry, and toolpath planning. We would like to underline one of the few works on the subject, which is Washmut's Considerations for Toolpath for Multiple Independent Extrusion Heads. Therefore, authors assume that the development of multiple extrusion manufacturing with the goal of reducing large part manufacturing time without compromising geometrical accuracy is worthy of studying. Current developments are studying the application of a thermal process in the C.M.S area to promote material coalescence. This work was supported by Fundação para a Ciência e Tecnologia through IDMEC. Nuno Frutuoso and Carlos Vicente gratefully acknowledged their research grants and the funding of the Big FDM project. Manuel Sardinha acknowledged the Mobile Pro U project for his research grant. Some of the references of this presentation. If you would like to know more about the research, please email me or find me in LinkedIn or ResearchGate. For now, thank you again for your attention.